All right, welcome back, everyone. We're a few minutes out from really getting started, so get comfy, grab something to drink, grab something to eat, a little snack, and we'll get started in the next few minutes. We'll get started in about 3 minutes, 3 minutes, and then we'll get started on the presentation of this notebook. Wait another few seconds just to let anyone else who's coming in a smidge late, another 30 seconds or so. All right, let's get the camera back on and let's get started with this session. We're going to dive into a real case study using mathematical optimization for disaster prepositioning of important resources. So just a couple quick sort of things I want to mention. If you have a question during this session, again, make sure to go to the Whova Q&A part of it and ask your questions there. I already see a couple have been answered. Great. So if you have questions, again, plop them there. There's no sort of hands-on coding this time. This is just sort of me um, walking through a notebook example that highlights the use of mathematical optimization for a really good cause. So don't worry about any of that. And I think All of these sort of housekeeping type of stuff that I want to go over. So, oh, I guess if you want to find the notebook, and sort of download it yourself, and look at it and everything, it is in the GitHub repository, which the link to that repository is also in the session details. You'll see several files here, and I also did a nice little zip, so you can just take care of that as well if you want just to download one thing, or you can download everything you see here, or fork, or do all the other cool GitHubby stuff that you can do to get access to this. Um, First off, so once you get to this, if you want to do it, if you want to sort of look into this now or while or after the presentation, sort of head back into this, here's the resources for that. Here is the beginning of the notebook itself. And before I really jump in, I just really want to say, I mean, first, I hope everyone had a chance to watch the video leading into this. It was definitely set the stage for what we're going to talk about in this notebook. So really gave a nice background of the ESIP's organization and what their missions are and what they're working on and how they're using, and sort of diving into a little bit of this case where we're just looking at how mathematical optimization can be used for a really good initiative. So I really want to say thanks to the whole ESIP's crew, for first just taking on such a great initiative, and putting something into place that may be really helpful to a lot of people in the future. So first, uh, thank you for just starting the work here. That's exceptional. But then also thank you for partnering with us here at Gurobi, and letting us help you tell your story about this. And we're just glad to be a very small part into the massive good that you all do. I also want to say thanks to Ben Rapkin, he interned with us for a little while, and he's the one who created pretty much everything you'll see. I'm here just sort of telling his story, of telling their story. So thanks for putting this together. And all of the work that you did. He did an exceptional job, sort of diving headfirst into this, taking on a lot of work and responsibility to get the story right, to get and put it in a way that we think is exceptionally great for new learners of optimization, um, and is a great starting place again to show the importance of mathematical optimization, but then also show how it can be used again in a really great scenario. So, one thing I also want to mention is this notebook, from a technical perspective, is also quite pared down to what to the actual Stockholm platform that was mentioned earlier, to what that actually sort of dives into and helps sort of assess, or will be used to help assess. We're focusing on just one little country, or one country here, which is a little portion of what the whole platform will consider. And eventually, as we get into the problem, we're going to even just dive into just one resource that is in question here. So we're going to be looking at a very small slice of what the capability is overall. So I just want you to keep that in mind as we sort of go through the notebook bit by bit, that the actual platform, the actual models, the actual data analysis, and the data, sort of putting everything together, is much more significant than what I'm going to be showing. But also to stay on that point, I did want to keep sort of I guess, like the essence of the project, of the problem, of the code, of the models and everything. Keep that sort of as close as possible to sort of what is actually implemented. So that didn't really quite work well in the Colab environment. So we're sort of just showing like the actual notebook, and not through Colab, because there's dependencies and things like that, and it's just easier and will work better this way. And the last thing I think I want to mention is this notebook, like I mentioned, is written for beginners. So some of it, as you if you may be reading through the text a little bit, may think like, yeah, this is sort of Opti 101 type of stuff, and particularly the way that we describe things and everything. Again, this overall is meant for a beginner. But there's two reasons why we felt that it was just a great thing to include in this training. One, it's not every day where you come across, implementations of mathematical optimization that potentially can have an impact like this one may. So we just really wanted to tell the story, and highlight it, because of that. But also from a technical perspective, some of the key concepts that I mentioned at the end of the previous video are in this, including the uncertainty aspect. And this model is sort of scenario based, and I'll talk about that, and we'll see that a little bit later. But so it just sort of is a nice follow on to some of the concepts that we wanted to talk about anyway. So again, and even I've been talking about how the problem from a technical side has been pared down for this presentation, and everything. The notebook itself is also trimmed down. There's a lot more to this that tells the story sort of from scratch, but we've already gone through that via video. So we didn't want to just clutter up the notebook with stuff that assuming you've watched the video before, it would just be sort of redundant information. Um, so we did sort of cut down on some of that, and there's also some more parts that are expanded upon, and we sort of cut out a little bit of it just for possible time constraints that we may have. So definitely want you to keep in mind that at some point, keep an eye out for a sort of a fuller release of this story, of this notebook, of everything you're about to see. And again, that's going to be something that we think is a great starting place for anyone getting involved in mathematical optimization, even if you're a true beginner or if you have some experience, because there's new things that this can sort of teach. So keep an eye out for when we're going to put this full thing out, for new learners, and yeah, and it's going to be great. So I think that's all of the sort of introductory type of stuff that I wanted to talk about. Just make sure that we're all on the same page, and the stage is properly set. Um, Again, just a couple more, just a quick another reminder. If you have a question while I'm chatting away, please go to the Whova app, or the web page. Go to this session, which is the optimization for good, hands-on example, emergency stock prepositioning. Go to that and submit the question there. That is the best way for us to see it and make sure that we get to it. So, I think I've gotten through everything I want to get through. I have my notes. I checked all those boxes. Let me make sure one more time. Yeah. So let's actually sort of dive into the notebook. So again, I sort of gave the links to it earlier. So if you have it open, awesome. If not, then just follow along. So essentially, we've already gone through the sort of the premise of the problem. So we're going to sort of dive into the data aspect of it. Let's look at the data that we have available. Let's look at the actually, I think this is a good. Yes, a good question. So this version of the notebook and all of the versions of the notebooks that we've pretty much run throughout all of Opti 101, 201, and 202, they're all usable, I think with the exception of maybe one. They're all usable with the quick little sort of pip install license. So it's a very limited version that you can do. Just you see sort of all these pip install Gurobi Pi, pip install Gurobi Pi. This one also fits under that as well, so you do not need to have a full license to run this. That said, um, as we sort of release this example and maybe and we may put together something that shows the full scope a little bit more accurately. In that case, you would need a full license. Um, and but if that's you and you want to look at the fuller version whenever that's released. If you are in academia, again, academic licenses are free, so you'd be able to view that easily and run that if that's your case. Good question. Thank you for reminding me to talk about that. I don't think I mentioned that really at all too much. So everything should be running in that smaller version of. So even if you're running it through like VS Code or anything else, again, just if you do quick pip install Gurobi Pi, you'll be able to run this. Okay. So that said, the environment that we use for this is a little bit more complicated. We are going to import Gurobi Pi, but there's a requirements text file that has a bunch of things that we want, so it's sort of hidden away there. And we also have a setup file that has a bunch of helper functions that are used in the actual production code of this. And so I wanted to keep that there so you could sort of see again like the a more accurate representation of the scope of the problem, um, and not have to dilute it or anything like that. So we first import all that good stuff. And again, as I mentioned, we are going to be only looking at one country. Again, the scope of the platform is much broader than this, but gotta boil it down for presentation. So we're going to look at Madagascar, and this is a country that's prone to natural disasters, cyclones, floods, droughts. You see a few of them there, all having a significant impact on the population there and make data-driven decision making really important. So these are just a couple of the helper functions that to get the data that we have. So I want to sort of show all sort of a bunch of these sort of criteria that we're looking at and that the platform looks at as a whole, excuse me. Depots, disasters, locations, probabilities, the items that we have, transport modes, inventories, different scenarios, distance matrices, and other bits of information that we use to help with this model and also as a whole for decision making. So I just wanted to show this part here because again, it sort of again shows a little bit more of the breadth of the problem. So there are some other aspects of the resources that we have, other things like weight and volume that may be useful as well, in addition to some of the other stuff that we saw above. So let's actually first look at a few visualizations to sort of let us know where things are. Whenever you're starting any project, the first thing that you do is exploratory data analysis and visualization. So let's start there as well. So this is just some code to give a representation of where the warehouses are and where a set of disasters occurred that we're going to sort of consider as scenarios. So you can sort of see in the blue dots here and here, these are where warehouses are, and the red dots are where sort of disasters of any type occurred. Um, and one thing I want to mention, I'll probably mention this a couple times, is some of this data, particularly the warehouse location, has been sort of randomized a little bit, just to be extra cautious about things like that. And anyone who's handling data out there, making sure that your data is secure and you're not leaking anything you don't want to, is always important. So we did that here. So essentially, this gives us a sense of where the disasters are and where the warehouses are. Some of them are very close to one another. And then also you have some warehouses that are sort of much more inland as well. Okay, so this just gives us a little bit of a layout of what's going on. So now we want to see what supplies are available. More code that extracts data and makes a nice little visualization that we have here, which sort of gives us a bar chart of saying, here's all of the resources that we need to consider and how many that we have. So we have buckets, water containers, mosquito nets, and so on and so forth, blankets, other clothes, and hygiene kits, and so on and so forth. So this gives us a sort of, hey, here's what we have available in this country, in Madagascar, and here's all the things that we're considering. Um, so one thing that I want to mention, essentially from here on out in the notebook, we are just going to talk about buckets as the item of interest. One of the sort of assumptions that we have is all of these all of the items sort of behave independently of one another. So if a disaster occurs, shipping buckets and mosquito nets and blankets, that all of that stuff is that they have no impact on one another. They're done independently. Um, so that is a sort of a natural assumption of the problem. And because of that, it makes it easier for us just to focus on one, because you would just then loop through this analysis however many times you need to look into all the different types of supplies that you want to look into. So let's find out where the supplies are. We talked about what the supplies are. Let's figure out where they are. So this is another visualization here. Nice little plotly, so we could sort of hover over and see where the buckets are, the location. Again, slightly randomized, but we can see where the main holdings are right now, and what values we have and where they're. So we get a sense of where the supplies are. So now we looked at the supplies, where they are, how much we have. Let's look at a visualization of where the disasters are. So the blue dots have now changed, so just so you know. So I look over to the right, you can see the key, the legend. These are the types of disasters. So we're looking at floods, storms, and epidemics are the three that sort of pop up here. We sort of see an approximate location of where they are, and this also gives us the information about the number of people impacted. So essentially, the each of the items sort of can service a certain number of people. So one of the sort of assumptions is if there's if there's a disaster and you need buckets, that essentially a bucket on average will be able to take care of 2.5 people, um, for the needs that they, for all those needs. So what this visualization shows, it's a little bit harder to see. So this is why I think, sort of downloading this yourself and taking a look is kind of is a good idea. We have overlapped for where the disasters are and and this is the supplies that are needed. So the red dot shows the number of people impacted. And the blue dot that's underneath it, it's kind of hard to see, shows, maybe this one's a little bit easier to see, shows sort of if you need, um, if a bucket services 2.5 people, this is that scaled version of that. So the number of buckets times 2.5. So this is sort of like, hey, this is how many, this is what we can, um, uh, this is what we can service given what we have. Um, and we can sort of see that there is a pretty big gap between that, which is not always great. So we can see that, there's a lot of visualization information here. And visualization is a key part, and this actually sort of came up a little bit earlier in Hassan's talk not too long ago about the importance of using visualization, not from, it's sort of a key thing from a data scientist's job perspective. It's something that you're definitely need to know how to do, and it's expected. Same thing for optimization. You need to be able to communicate your results, and communicating your results visually is very, very helpful. And that's what the Stockholm platform is there to do. And we're going to sort of look at a couple versions. One is an early version, which was super crucial in getting buy-in and helping communicate results. And as we all know, many of us have probably worked with a lot of visualizations and have had to use them to to get projects rolling, or to get buy-in and things like that. you start with what you got. You start with the skill sets you have, you start with the tools you have to get what you want out the door first. But then there's always constant iteration, constant improvement, and the Stockholm platform is no different. They've made tremendous strides over a relatively short amount of time. And going, this is just sort of showing an initial version of the platform. And now, after a few iterations, now and incorporating newer technologies and everything like that, now you sort of see something that's a little bit more robust and something that gives us a lot more information right at our fingertips, right at our eye. You can see it right away. Um, and is a really great way to communicate what's happening maybe in a particular country or what the scenario is. So this is just a quick screen cap of what the platform looks like uh, pretty much to date. You can see things like this again, this is for Madagascar. As you can see again, randomized sort of storage facilities and then disasters by type and the number of people affected over time and just a whole bunch of possibly useful information. So I think have set the stage enough with what the problem is all about, what kind of data that we have available to us, what it looks like, what the scenario is. So now we can actually sort of dive into the optimization models. And we're going to do this sort of bit by bit. Some of this may seem a little bit elementary again, because this is again, I'm presenting this as something that is really good for beginners and intermediates as well. But it is helpful to sort of build a little bit to help get to the end model that is sort of, are going to be our stopping point. If I just sort of jumped into that, yeah. It's just a little bit better to sort of build bit by bit, and then it makes things a little bit more clear. So let's get into some math notation. I know it's been a lot, it's been enough time before we saw some, summation symbols and subscripts and all that sort of stuff. So I apologize for taking this long to get back to the math. So let's introduce some of our key, our decision variables, parameters, and things of that nature. So we're going to let tau ij be the time to ship a single item from warehouse I to a particular disaster. So this is in this scenario, I guess I should back up maybe a smidge. In this scenario, we're sort of just considering one particular disaster, and then we're going to build on top of that by talking about all possible disasters, and then talk about sort of expanding the problem bit by bit, like I was mentioning before. Here we're going to start with just one disaster and see how can we best ship things to meet the needs there. So tau ij is that time to ship. And another bit is we're going to talk about, I'm going to say time a lot, but just replace time with cost because we're sort of assuming that time and cost are sort of interchangeable. It's some cost vector, be it time times something or whatever it is. I'm going to keep saying time, but just so you know that that those two things are sort of replaceable at this point. Oops. So, let Y be the amount of the supplies that we send, and XI is the starting inventory at each warehouse, and D is the demand for the item. Um, here is our optimization problem from a very, very basic concept of it. And again, put some notes in here about how mathematical optimization assumes non-negativity for your decision variables. We all know that well and good by now. Here is the code to solve, and we optimize. So essentially taking our nice little problem here, writing in some of the code. And just a couple of things I want to highlight about the code here. Supplies, we don't say buckets per se. We're working with particular one supply of buckets. So that's what's happening here. So you just sort of explaining that. We have our objective, and let's fire up the solver and optimize. Let's look at the results, extract and everything. Again, we've probably seen a bunch of different ways to get the results of an optimization problem. a bunch of ways to do it. So whatever suits your fancy. But again, given that very simple optimization problem, you might be thinking this is a bit overkill. We don't need to use mathematical optimization for this. And you're right. Essentially, if you just started sorting um, and and you look at the amount that is sent from and the amount that we allow, sort of the xi, you just sort by distance and then just do a greedy, sort of a greedy approach there. Um, that will suffice here. That's perfectly, that's fine. But as we all know, now that we're intermediate level to possibly expert to maybe even super expert optimization modelers, at this point, we know that life is not this simple, that the decisions are not this simple, and that we actually need to be more complex. So instead of preparing for one disaster, we prepare for all of the disasters that may occur. So we're going to take this to from one scenario to all of the scenarios that we want to consider. Um, so this is going to help us take into consideration that uncertainty. So again, scenario-based optimization here. So let's include um, all of the disaster types and all the location and sort of considering several locations. So scenario K with the disaster located at J, the time to send Y supplies from warehouse I. That was a bit of a mouthful. Take a second to digest that. Okay. Scenario K with the disaster located at spot J, the time for warehouse I to send YI items is tau ij yik. Um, Saying it out loud again and again just makes it a little bit more interesting. Anyways, repeating for all the warehouses, summing, so sum over I for that, and repeating for all disasters, sum over K, sum I, tau ij, and everything. So at this point, now let's sort of start accounting for the randomness here, so accounting for the uncertainty. So one of the things that we talked about earlier in the uncertainty presentation is expected value. And that's the approach that this problem takes is let's um, let's minimize the expected cost. Let's minimize and again the one way that we want to make sure that we interpret expected value, particularly in this scenario, is again it is a long run average. So keeping that in mind. Um, I did want to sort of just give a little bit of we didn't talk about expected value, and I don't want to assume that everyone has been has a lot of experience in that type of in this type of probability and statistical stuff. So I just want to sort of go through it quickly. Um, the expected value is I mentioned this very briefly in the uncertainty video, but let's sort of see it a little bit more so it's a little bit more clear for anyone who's not super familiar. If we have a discrete probability distribution, then it is then the expected value is the probability of a certain outcome I happening times the value of that outcome. Sum it all up. There you go. There's your average. So we typically think of these as simple games like rolling a hopefully fair six-sided die. We have a couple just examples here just to make sure that you kind of understand how this all comes together if you're unfamiliar. Um, I'll skip through it a little bit. Let's talk about, we have one about a fair six-sided die, the flipping two coins, talking about what the expected value is there, and then drawing cards. These are always your, rolling die, cards and coins are somehow always the first expected value problems that you'll always see, but um, but they help get the case. They help get the point across. So let's see. Let's move on to the model where we start to actually incorporate the probability of a certain disaster. So let's sort of build this model piece by piece. So let PK be the probability of disaster K, and TK be the total travel time involved for disaster K, just as we sort of outlined in the previous section. So our expected value that we just talked about is the expected time, which again is the expected cost, which again is a long run average, is the sum over K, PK, TK. So but we've already discussed what the TK is in terms of the tau and Y. So let's just replace that, make that substitution. And this is an expression for the expected value again, for the expected time or expected cost. And so now that is what we want to minimize. That is our objective. So here we go. Here's our objective value, where or excuse me, our objective function that is an expected value. And the constraints are pretty much unchanged as well. And uh, again, what we're going to assume, we're assuming two things is we have a sort of a fixed, that this xi is a fixed value, um, is a constant, and then the probability is sort of just uniform amongst all of the disasters that we have in the database. So each of them are equally likely at this point. So we can run this. And again, the code doesn't expand by too much. And print out the decision variables after we optimize. And this gives us our solution. I'm doing pretty good on time. So we just talked about, there's a lot of text on here. I'm going to sort of just highlight it really, but I wanted to keep it there because and I wanted to have it there for you guys to review if you want to come back to this. Because we just talked about probability. We talked about several things that you can probably see as like, hey, this is, you know, there's a lot of uncertainty here. There's some ways that I think, predictive analytics or even just descriptive or whatever it may be, data analysis, modeling, other things like that, um, may be very important. Um, whoops, I opened up the chat and it popped here. There we go. I saw chat things popping up, so I'm gonna make sure I didn't miss anything. But again, another reminder, uh, the session information in Huva has the link to the GitHub repository, which has this file, which there's also a zip file that has everything you need to run this as well. So that's all there. Just a quick reminder. So there's a lot of things about, hey, there's uncertainty here. There's things that I think that could be expanded upon. Maybe there's other, So what this section is just like, hey, there's a bunch of ways that right now data science can really help um, a problem like this can really influence what's going on and can really add value to this. So I'm not going to read through all of these, but things like time series modeling, geospatial data analysis, which is something that is extremely valuable, and I've done a lot of it in my career before coming to Gurobi, and it's something that has always been challenging yet very very I guess rewarding or very, very helpful in terms of answering questions because it's something that's difficult to deal with, but can be very, very helpful. So there's some things here, and I'll sort of just probably let you read this all on your own if you want to come back to this as well. So Um, let's put this all together and talk about optimizing the allocation and transportation. So essentially, we've assumed this xi here, because again, this yi is going to be the amount that we send of buckets. Again, this is only looking at buckets at this point. Again, we're assuming all of these resources, all of these items behave independently. That this y is the amount that we're gonna send. And this xi here up until now has been a constant. But hey, let's make but that seems like a good thing that we should be able to decide. Like how much should we put here, you know? So this is a new a new way of looking at the problem. So let's make xi a decision variable. So essentially this sort of changes our overall um, optimization model, but not by a lot. There's a lot of, sort of going through this step by step, but I'm pretty sure by now you guys have, everyone listening has sort of figured out, okay, this is exactly what's going on. But here is the whole model now. We have all we're doing from the previous model to this one is adding in that the capability for this one right-hand side to go from um, a constant value to a decision variable. But now we then need to add a constraint that talks about the total supply that we have for this particular item. So we're minimizing the total expected cost. We need to meet demand. We cannot send more than the warehouse has, but now this is something that we can decide how much this warehouse has. And this is again for each scenario. And but we do have an overall limit. We can only allocate the total amount that we have. So this is the new parameter here is the total amount of, in this case, buckets that we have to allocate. So part of our decision is where do we put them, and then from there, it's um, how do we then distribute them. So the code doesn't change by all that much. Um, we need to, here's where we add our new decision variable, and that's about it. And we also have this total constraint as well. So this is when we put the number there to make sure we sort of highlight that this is right right here and right there. There we go. And then voila, we run this and extract um, the solution. Here we go. And and that's it. I do want to talk about a couple more bits of information, but that is the model that we have as of now. There is kind of a little bit of homework, I guess, that I'll talk about in a minute, but I first want to go over a few tidbits here. Um, so again, the cost, if you think about the cost of things, and this sort of relays into a little bit of an expansion of the model to get to like its true final form. But we sort of leave the true final form to you to sort of work through a little bit. Um, the cost that it take, we haven't talked about how you get things from location I to J. We've just said these are the two locations, but we didn't consider various options. And if you remember at the beginning, I sort of talked about if you sort of talk or I was talking about this at the beginning of different modes of transport. I mentioned that early on. And that's some of the information that we have uh, that was read in. Here's where that comes into play because there may be taking flying things via taking via air can be much more expensive than maybe by truck. But if your roads are damaged or destroyed, then a truck won't work. So there is there's a balance. There's there's some assumptions and there's some things you need to consider when it comes to the mode of transportation. So that is what this section sort of starts talking about, where we introduce a new subscript R. And that is R has to do with the mode of transportation. So all we really see is not much, again, changes. We're adding a couple subscripts. Now our Y decision variable is um, the amount that we're going to ship from location I to for disaster K by mode R. So now we just have a few more options there, and our model stays pretty much the same. But again, when we see this additional summation here, we're just sort of, again, there's just more we've noticed from small model to medium to kind of almost there to this is like the final. All we're doing is just adding a little bit here and there. So that is something that you can implement and see how that goes. And hopefully that works out pretty well, given we're all pretty good at writing Gurobi Pi now, I would assume. So let's sort of understanding the solution is very important. Again, this is something that needs to be communicated throughout any optimization problem, but any analytics problem and any problem whatsoever is, all right, I have a solution. How do I communicate it? Um, so what is done in here there are many criteria and metrics that are looked at through this for this problem. We're just going to sort of highlight one for now, and it's called essentially a balance metric, and it more or less is just the ratio of a current inventory allocation. So that's um, and essentially how does that um, how would that inventory allocation sort of respond, or what would the cost be or the time be for a scenario there with the current allocation versus what we would say to be the optimal given this model. So it's current case versus compared to best case to optimal case. So that is essentially what this metric provides is that value. So you could just sort of see um, get some information about how far off you may be. And again, thinking about how this isn't just done for one resource. This is done again, keeping in mind the whole context of the problem is very important here. uh, many more countries with many more with all of the resources considered, sort of you get a full view of what's going on. So this balance metric, while seemingly simple right now, again, in the whole scope of things, can be very important to help you understand, oh, this particular resource in this particular area, this one's way out of line, way imbalanced. So this is maybe where we need to start focusing some efforts here. So this is something that can be used as a way to guide decision making to help out improvements. So so that's how this interpretation of that's how the balance metric, what it is and sort of how it's used a little bit at this point. So um, let's see. I think that's probably pretty much everything I want to talk about. We get done a little bit early here. I think that's a-okay. Feel free. I've seen a couple more questions come up in the chat, and feel free to put any more in there. But I think I don't see any that I'm gonna answer at the moment. So I think what we can do is I'll sort of end this session a little early. If you haven't noticed, my voice is starting to go. So I might take a little sip of tea or something, although I don't have to speak anymore. But it was great be to go through this notebook, definitely take the time to learn a little bit more about this awesome problem with this awesome model and understand this complex platform and everything that it's doing to really uh, do some good. So I think we'll end it here, and there's a couple more sessions for you to check out. I guess what I can do is reference or make sure that everyone's on the same page there for that. Um, the next session, which is going to start in about I think 13 minutes or so, is a just a nice wrap up of everything that we discussed. And again, talking about some next steps for you as intermediate to expert level optimization modelers now, what you can still do to keep going on your journey. And then there's also a session about how generative AI and mathematical optimization sort of can come together to do some really, really awesome stuff. And some efforts that we at Gurobi have made to make learning mathematical optimization open to people via generative AI. Because if you're watching me right now, and if you've probably coded anything in the last couple days, probably an 80% chance that you ran it through Chat GPT or asked for some base code for or something like that. Everyone's doing it, so we gave some guardrails. So definitely check out that presentation as well. And yeah, I think that'll be it for now. So thank you so much for hanging out with me, and I'll see you all later.